In this slide, we will learn about another statistical feature, which is called confidence interval. So one of the primary aims of the statistics is to estimate the properties of a population based on a limited sample drawn from that population. And statistical inference is basically estimating statistical properties from a limited sample. But if you have a limited sample, then you will not be able to sure if it is coming from a certain population or certain distribution. That's why this kind of confidence intervals are developed. And the interval estimator definition is the estimated range of values within which the parameter is expected to lie within a given probability. And this is important for us. This is actually the confidence interval. When we have a limited data, limited sample, then we will have some interval to increase our confidence on having that it is coming from a given probability. And there are two types of this, one-sided interval and two-sided interval. In the one-sided interval, we have the confidence that the parameter estimate is less than or greater than the true value. So it can be either less or greater than a true value. So it will be one-sided because it's either less or greater. On the two-sided interval, on the other hand, both less and greater will come together, and the estimate agrees with the truth with no consideration to the sign of discrepancy, or not considering to be either less or greater. And because this is more general, we will focus on the two-sided interval. This is preferred because we have two sides, lower and upper, and we can have a confidence interval with two sides. We also need to define the central limit theorem to continue on the confidence intervals because we will have a limited sample and we will have a confidence on that limited sample which comes from a certain distribution, and that distribution is usually normal distribution according to the central limit theorem. If we go into the definition of it, if the true variance of the distribution of y, which is the data, and the variance is the sigma square, if this is known, true variance, not the estimated variance, a true variance is known, the sample mean, which is this, comes from a normal distribution with a true mean. So we have a true mean and a standard deviation or variance, which is true as well. Also, we have some limited sample and we have a mean from that limited sample, which is different from the true mean, because with this limited sample, let's say 10 samples, we will have a different value from the true mean. But this theorem says still the sample mean comes from a normal distribution with true mean and variance divided by n. But the problem is we don't know the true mean and we only know the mean of the samples. And basically the idea can be, so the true mean and sample mean idea is coming from actually from n sample to infinite sample. The sample mean goes to true mean. So true mean for infinite sample, or for a enough number of sample if we have, then we can have the true mean, a large number of samples actually. Similarly, for the standard deviation or variance, this is the variance for the certain limited number of samples. This is the true variance for infinite or enough samples. And this central limit theorem says the sample mean actually comes from a normal distribution with true mean and true variance. That's the basic idea. And you know that this bell shape is the normal distribution. So there are some other definitions of central limit theorem. Let's check that too. Distribution of means. So this is sample mean. Actually, we have sample means, but let's say we have enough samples to obtain the true mean, and we actually take a certain limited number of samples from those infinite samples, let's say, and each group of samples will have a different sample mean. So distribution of means that we take from different sample groups, let's say, is also normally distributed regardless of the distribution of the random variable. So even though the actual distribution is different from normal distribution, if we take the means from a certain group, of limited samples and take the distribution of it, it will be normally distributed according to the central limit theorem. And with the increase of n, the number of samples, the variance of means approaches to 0. So because when we increase the n, actually the mean will approach to the true mean. That's why the variance will be 0. And when we have a large n, or number of samples, the random variable z in the distribution of means is standard normal. So we will have the distribution of means that we mentioned in the first part, and the random variables we are taking from that samples is standard normal. Standard normal means actually a normalization of a certain distribution to the value of mean 0 and standard deviation 1. You can see here the bottom part, the B part, is the standardized version of the normal distribution. We still have this bell shape here, but it is between, actually with mean 0 and standard deviation 1. If you remember, this one standard deviation only 68% of the data. And maybe 2 standard deviation will be 95. But so we will have some interval, lower and upper for the mean. And we can, if we go to the standard deviation part, it will be lower upper will be defined as z alpha divided by 2 and z minus alpha divided by 2. And we will have the standard normal estimate for this graph as a normalized way. This is the sample mean, this is the true mean, this is the true standard deviation, and this is the number of samples. When we use this formulation, it gives us the standard normal estimate from this this axis, actually normalized axis. And the probability that the true mean of y, which is mu, falls within the bound from L to U is 1 minus a. So basically we assume that, so we don't know the true mean, we have a sample mean, and we will have a lower and upper bound for the true mean. Because we don't know it, we can have just some interval for estimating the true mean. And this lower and upper bounds, when we normalize them, these will be actually between so the distance here will be 1 minus alpha, and this part is alpha divided by 2, and this part is alpha divided by 2. And this is defined as the probability that the true mean is between lower and upper bounds is 1 minus alpha. And this is called a two-sided interval. So we will talk about this a little bit more in the following slide. And this is called the significance level. Actually, it defines the probability that the mean value, true mean, is between lower and upper bound. And this significance level can change, and it depends on the statistician or the user. Actually, we decide this. Usually it is used as 0.05. That's why we will have 1 minus 0.05, 0.95 times 100, 95% confidence interval probability, let's say. Now, with the definition of this probability that the mean is between lower and upper bound is 1 minus a, a two-sided confidence interval. So this is actually the two-sided interval, and for the standard normalized axis, we can have two sides as this one. So this is the standard samples formulation that we showed in the previous slide. We can simply have a smaller or larger values. Basically, these blue areas are these. So minus z alpha divided by 2 and z alpha divided by 2. This part and this part we can think of. These two sides. And z alpha divided by 2 is a standard normal variable. So this is basically this value. And this is the distance measured along the normalized axis above and below the mean that encompasses 1 minus alpha probability. And the values of z alpha divided by 2, basically the z values here for the normalized axis, are actually tabulated in statistical books or calculated using functions in software packages. Even in MATLAB or Excel, you can simply enter this alpha value and simply have the z value from they can provide you the z value from a tabulated data. Actually, it is readily available. They already listed them, so you don't need to calculate this. Just get it from the table or the software. As an example, let's say we have 0.05 alpha. In other words, defining an interval encompassing 95% that I mentioned in the previous slide as well. And z alpha divided by 2 is equal to about 196 from the tables or software package. It will give this to us. If you enter 95% or alpha equals 0.05, it will give us this z value. And this means that an interval around the mean of the width is plus minus 1.96 times the standard deviation will encompass approximately 95% of the distribution. What it means is that we have the mean, and the lower and upper bound will have a 95% coverage for the distribution, we can say. And it is basically mean times 1.95 times to the right and 1.95 times to the left. So for these lower and upper bounds, if we isolate mu's, we can get a lower bound for mu and upper bound for mu. Actually, this is the lower bound. If we isolate this, you can see here, this was the mu actually, but for mu we actually are having the lower bound. Simply isolate this, so multiply this by this one, as you can see here, and move it to other side. Y minus this becomes the lower bound. And with this, the same, isolate this mu and set it as u. So these two are the left and right sides of the mean value with the determined alpha significance level, and we obtain this from table. Then this is the true standard deviation, and this is the sample mean. From here now we will have a range for the true mean. So here the problem is we have the true variance. We need to know the true variance here. But in reality, we don't, because we don't know the mean, we don't know the true variance either. So this true mean, we don't know that. We don't know the true variance either. So what can we do in that scenario? Let's go to the next slide and see that. As we mentioned in the previous slide, the true variance is used to be able to get these upper and lower bounds. So sample mean and true variance. But in reality, we don't know the true variance. We only know the estimated variance, SY. So a simple modification is that instead of using the sigma, let's use SY. That's the sample variance or standard deviation. And in that scenario, because we don't know any true values, we only use the sample standard deviation. The random variables are not coming from a normal distribution anymore. They are coming from another distribution, and it's called T distribution. That's why it's shown by T. And it's also called student T distribution. And the lower bound and upper bounds also, instead of using sigmas, we just use SY. And now we will have sample mean and sample standard deviation. And these values are not from Z tables, but from T tables, from the T distribution tables now. So this T distribution is different from normal distribution now because we have limited samples. And this was developed by statisticians saying that, okay, when we have limited samples, we don't have the standard normal distribution, but a T distribution. So yeah, T is the standard random variable for the T distribution for a probability of alpha divided by 2. Its values are also tabulated in statistical books for different number of samples, and n-1 is important here, and also can be calculated using software packages such as MATLAB or Excel and libraries, similar to the case for Z alpha divided by 2. For example, if alpha is 0.05, then and the number of samples is 20, then T is here 0.05 divided by 2, and this is 19. When we check the table for this, it's 2.086, basically. And let's talk about the T distribution a little bit. As we said, because we have a limited sample, it doesn't represent the actual normal distribution of the data with the true mean and true standard deviation. So the 2t distribution can be thought of as a modification of the normal distribution that accounts for the fact that we have an imperfect estimate of the standard deviation because we have limited data. So when data number n is small, it tends to be flatter than the normal. So you can see this thin line is the actual normal distribution, and when the number of samples are reduced, like the dashed is n equals 6 for instance, and the thick one is n equals 3, you can see the peak point is getting lower and lower. So it's getting flatter. And from the right and left sides, it's getting a little bit higher, but it will be flat eventually for one value. So for small number of measurements, it yields wider n, hence more conservative confidence intervals. And as n grows larger, the t distribution converges on the normal. So we will have this t distribution for different number of samples, different values, and those are tabulated. So this curve is the comparison of the normal distribution with t distribution for n equals to n equals 6. So the t distribution is getting generally flatter, as you can see here. So let's see this in an example, how to use this information for t and the confidence intervals.